Hello, in this video I will be discussing about the peculiar shape of dz² orbital and its electron density distribution in their lobes. It has a different shape than the other 4d orbitals and also electron density distribution too. There are 5d orbitals, dxy, dyz, and dzx. All of these have their electron density in between the axes, whereas dx²-y² has electron density lobes along the axes x and y respectively, whereas dz² has a little bit different shape. All of them I have talked about have double dumbbell shape, whereas dz² is having a different shape. It has two lobes along the z-axis, electron density lobes along the z-axis, and a electron density ring in the xy plane. The electron density resembles with a donut, and the electron density lobes along the z-axis resembles like a dumbbell that are at gym. So totally it can be said that it is a donut dumbbell shape. So what about electron density distribution? The electron density distribution along the z-axis is 2/3 of the total electron density, whereas in electron ring density it is 1/3 of the total, whereas in case of other 4d orbitals each lobe is having 1/4 electron density distribution. It means they are uniformly distributed. The electron density is uniform, but in case of dz² orbital it is not uniform. So this video is all about that.
So what could be the solution to this problem? Only the solution to this problem is that we can assume that the dz² orbital is formed by the combination of two atomic orbitals. Those are dz² minus x², dz² minus y². When they combine together to give dz² orbital. So dz² orbital. Now why we are taking only these two orbitals? So let's discuss about that. For example, when we talk about the p orbitals, they are of three types: px, py, and pz. It means symmetrically distributed. All the axes, all the three axes are having the lobes. Now move to d orbital. D orbitals are of five types. One is dxy. It means the electron density is between the x and y axes. dyz means the electron density is between the y and z axes. And the last one, dzx. In all of these three, the electron density is between the axes xy, yz, and zx respectively. While the fourth one is dx² minus y². In this, the electron density is along the axes, x-axis and the y-axis. Now, last one, the dz². Now, you would observe that these are symmetrically x, y, yz, and zx. Here, x² minus y² is there. But what about dz² minus x² and dz² minus y²? These are also the possibilities, because the nature loves symmetry. And here also be symmetrical. When the xy is existing, yz will also exist, and zx is also existing. So x² minus y² is existing, they must also exist. So here the idea came that dz² is the combination of these two orbitals. According to linear combination of atomic orbitals, we consider them to be like this: psi1 wave function of this orbital and psi2 the wave function of this orbital. When we combine them together, we will get the dz² orbital. Now this and this. Now dx² minus y² will combine with this. Now what will you get? This figure. This is equivalent to the dz² orbital. Let's see this from the above. From above, this and this. These orbital will look like this, and these are forming like an electron density ring. And now you can see here that the electron density is combining or meeting at the same space. It means the electron density will be increased there, and this electron density is not combining, not getting combined. They are at the different places. Hence, the electron density at this lobe, at the z-axis, is 2/3. It means it is higher than the electron density in the ring, 1/3. So both the figure, how it is different from the other d orbitals, and also their electron density distribution can be explained through this. Thank you.